Good morning, good afternoon, good evening, everybody. Thank you so much for connecting today for this seminar from NfoLD, the Network for Light Detection. NfoLD is a research coordination network from the NASA Astrobiology program, whose goal is to bring together scientists and engineers and those interested in technology for light detection. And the purpose of these seminars is to bring experts to talk to us about their advancements. We have these seminars typically every other month, but if you're interested in speaking at this seminar, please contact us at contact.nfold@gmail.com, and we'll be sure to schedule you. Today, we're really lucky to have Dr. Ricardo Arevalo join us from the University of Maryland. He will be speaking to us about laser desorption mass spectrometry with an Orbitrap trademark for planetary exploration. Ricky, really grateful that you took the time to speak to us today, and really excited for your talk. The floor is yours.
Thanks. I appreciate the invitation. You can make fun of the trademark, but I always get in trouble when I don't put it on there. So one of our collaborators is the inventor of the Orbitrap, and every time I used to forget to put it up there. So now I know all the rules about it. You only have to put it up there the first time, though. That's what he told me. So yeah, so thanks for the invitation. I'm going to share with you guys some work that my lab has done. So the M-Class Laboratory, it's a fancy acronym because I am a derivative of NASA. I spent my first 7 years of my post-PhD life at NASA Goddard Space Flight Center. So M-Class is measurement of composition via laser ablation, sampling, and spectrometry. It's worth going into the acronym because that's just what I'm super interested in, and that's what a lot of what we do in my lab is laser processing and mass spectrometry. And so today I'm gonna talk to you about one kind of research line, probably our biggest research line in the M-Class lab, which is interfacing an Orbitrap mass analyzer with a laser desorption system. Let's see if I can get this to go. Boom. Okay, I wanna get that laser thing off. There we go, okay. So this is NfoLD. So you guys are probably somehow interested or already integrated with the astrobiology community. I'm an amateur astrobiologist, but I'm growing in that capacity. I'm happy to say that when I went to my first AbSciCon, which was, I forget when that was, 2015, it seemed to me like I wasn't a freak, as in a lot of us astrobiologists come from different backgrounds. I didn't meet a lot of astrobiologists that had astrobiology degrees, for example. And so I'm going to try to contribute, and you'll see where my knowledge rolls off in this. But my background is traditionally, it's in geology, geochemistry, trace element geochemistry, but I used mass spectrometers for my PhD. When I went to NASA Goddard, I became part of the MOMA instrument, the Mars Organic Molecule Analyzer, which is set to fly on the ExoMars rover later this year. So you'll hear a little bit about that. But what's kind of like the common theme between what I did historically as a geochemist and what I'm doing now as a planetary scientist and as an amateur astrobiologist is laser desorption mass spectrometry. So using a laser to access the chemistry of a sample and using a mass analyzer to tell us information about the composition. And so I wanted to set the stage. I realize that actually I don't want to say most, a lot of those that are listening might not be mass spectrometrists or might not be laser people. And so I thought I'd set the stage. So I put this pretty graphic up here. My senior graduate student, Grace Nee, made this graphic for a review paper that we wrote together last year. Many of you guys may know her. She's very active in NfoLD. And she's a delight to work with. And she obviously makes very nice visual graphics that help to convey a lot of information. So I wanted to start this, right? This is slide 1. I wanted to set the stage for this by saying, here's a historical perspective of mass spectrometers that have flown into space for planetary applications. What do I want you to take away from this? There's a legacy of mass spectrometry in space. So really, we've learned a lot about the inner and outer reaches of the solar systems from mass spectrometers. Of those mass spectrometers, most of them, you can kind of see it here, most of them are of the quadrupole variety. And so My talk is going to tell you about what my team and I have been trying to advance. We're trying to advance the state of the art. But anyone who's trying to advance the state of the art needs to compare that next generation technology to legacy, to heritage. And so I'm going to do that today and try to inform you why we're so excited about what we're doing by comparing it relative to quadruple mass spectrometers, which have flown for decades. I wanted to make sure and say that quadruples and mass spectrometers in general aren't just historical instruments. So here's the most recent snapshot of the planetary fleet. So any NASA headquarters person usually starts out their talks with one of these beautiful graphics that shows the current state of different planetary missions. And what I've circled or rounded edged squared here are the different missions, many of which you might be familiar with, that have mass spectrometers. So they continue to be a go-to analytical instrument for planetary science. But again, what I'm challenged to do, what any of us that are interested in pushing the envelope of technology, what we're all challenged to do is to compare our instrument to legacy. And so heritage is the quadruple. And as I mentioned before, quadruples have been our go-to means to explore the solar system for over 50 years. There are still a lot of advantages related to quadruple mass spectrometry, advantages that allow them to still be proposed and still be implemented on current and future missions. For example, Da Vinci to Venus has a quadruple mass spec on it, and that's going to fly in the next couple of years. Anyway, so what they have in common, these quadruple mass specs, is they're low cost because they have so much heritage, because they've flown since the 1960s. The core instrument itself hasn't changed a lot. You can look at a rod assembly from the Viking era and compare it to the rods on the SAM instrument on Curiosity. The dimensions have changed, but they're still hyperbolic rods. And so there's just not a lot to reinvent there. Because of that, there's a lot of technical maturity. They've been ruggedized and they've been deployed to a variety of planetary environments, landers, atmospheric explorers, exospheres, etc. So we understand the science that they provide, and it is a rich amount of science. That being said, since the 1960s, there's been a lot of time and a lot of money invested in maturing alternative mass analyzers that bring other analytical advantages to the table. So those advantages that I'm going to focus on today are what I'm going to call molecular disambiguation and innovative sample handling. So the capacity to interface to different ion sources. The reason I've got a little asterisk next to molecular disambiguation, this is kind of a little teaser here, is that we're still talking about mass spectrometers. And even though we've got this wealth, we've received this wealth of information from quadruple mass spectrometers, such as, here's a traditional spectrum that I'm not the only one who highlights. This is like everyone's, in my experience, this is like everyone's favorite Cassini INMS spectrum. You can see that we can derive a lot of chemical information here. We've just got intensity on the y-axis, mass to charge ratio on the x-axis. And we can make a lot of inferences as to what we think is underneath each one of those peaks. But the peaks in this mass spectrum are fat. They're unit mass resolution. So we can't with 100% confidence say that we know 100% of this peak is a hydrocarbon. 100% of this peak is a noble gas. There's a variety of isobaric interferences that could be hidden underneath each one of these peaks. So how do we build, this isn't a new problem here. How do we build confidence in what we think we're seeing? Well, there's a lot of people in our community, maybe people who are listening to this presentation right now, that look at diagnostic fragmentation patterns, diagnostic isotope abundances to try to reconstruct the observed relative distribution of the peaks in that mass spectrum. Of course, if you have a complementary instrument on board your spacecraft, so here we have the Cassini infrared spectrometer, you can have corroborative identification of different chemical components that you might observe in that planetary environment. But this is a problem that that we have faced and we will continue to face in the coming decades. Separating out and trying to elucidate as much information as we can from that mass spectrum. Again, it's not new. So, you know, even in addition to trying to reconstruct the spectra, we get other people, other groups. My group historically has pursued other analytical techniques that can allow you to kind of circumvent those gymnastics, the spectral gymnastics. For example, if you have the capacity to fly a gas chromatograph, now you have a different way that you might be able to separate chemical compounds that otherwise may represent isobaric interferences with one another. So the SAM instrument, this is a snapshot of Carolyn's paper on the SAM instrument showing the separation of chemical compounds based on their diagnostic retention times. I was part of the MOMA instrument development team. So I was the product development lead for the mass spectrometer. MOMA, it enables tandem mass spectrometry. If you're a spectrometrist, a mass spectrometrist, you might know what that is. What it means is that if you see, let's get my little laser pointer here. If you see a particular peak of interest, what you can do is you can isolate it. So you can eject the stuff that you're less interested in at the moment and enrich the signal of that chemical compound. And then you can break it. You can break it on purpose to derive information about the structure of that compound. And if you derive the structure, you can hopefully build your confidence in your molecular assignment. An alternative way of trying to elucidate more information from a mass spectrum is to increase the mass resolving power. So here you make a fat peak so skinny that any isobar, so chemical compounds that have similar mass to charge ratios, are effectively resolved from one another. And so here's an example spectrum that I tend to show, which is a single extract from the Murchison meteorite analyzed with an ultra-high resolution. It's a laboratory instrument, but it's an ultra-high res mass analyzer. And what you can see are peaks within peaks within peaks. This team saw over 40,000 molecular identities in the single extract of a single meteorite using this mass analyzer. That's a lot of complexity that otherwise might be masked with a more limited mass analyzer. I hate saying the word limited. There are other ways that you can separate isobaric interferences too. I just don't have the time to go over them. But what my group and I are interested in is really kind of pushing the envelope with mass resolving power. And so here we're trying to distinguish, again, chemical compounds with similar mass to charge ratios. So again, we're challenged to compare ourselves to heritage, to legacy. And so traditional quadrupole instruments have a mass resolving power of m over delta m, if you're familiar with that notation, of 500. Okay, that's a bar. That's a bar. My group's not the only one trying to advance the state of the art with regard to mass resolving power. Other spaceflight instruments have already flown higher, what I would call medium to approaching high-res mass analyzers. So the Rosina instrument on board the Rosetta spacecraft had more than 10x higher mass resolving power than a quadrupole mass spec. And then the mass specs instrument, which is a multi-bounce time of flight that's going to fly in the Europa Clipper mission, offers even higher mass resolving powers. The Orbitrap, however, if you've had an opportunity to work with one of these instruments in a commercial setting, they can exceed the mass resolving power of any flight instrument or any instrument currently in formulation for a spaceflight mission. And so that's what we're trying to ruggedize for spaceflight applications. Okay, so what do we want to do with that Orbitrap? We want to interface it to a laser. It's a relatively simple ion source, but it brings a lot of science to the table. So first and foremost, as astrobiologists, or in my case, an amateur astrobiologist, an advantage of a laser source is that you actually don't need physical contact with the sample. So it kind of relaxes requirements related to planetary protection. That's kind of a neat thing on the side. But on top of that, laser methods, whether in the commercial, industrial, academic, whatever realm, provide semi-quantitative information of both organic and inorganic information. That's really a powerful thing that you get. And because it's a microbeam technique, you get spatially resolved measurements, with the spatial resolution being limited primarily by the footprint of your laser beam at the sample of the surface that you're trying to characterize. On top of that, it's laser desorption and laser ablation techniques they're destructive, but they're far less destructive than some of the techniques that we've flown today. So for example, pyrolysis, when SAM pyrolyzes a sample, it's typically tens of milligrams, typically. Whereas a laser, every single laser shot, at least our instrument gets, every laser shot gives you a full mass spectrum, and each laser shot only removes a nanogram of material. So it's far more sensitive with regard to how much mass you need to excise or destroy to get your mass spectrum. And then on top of that, with a laser source, if you have the capacity to fly an overqualified laser source, something that provides more energy than you need to just ionize your sample, you can do some fancy things. And so if you have a really powerful laser system, you can exceed the desorption and or the ionization threshold of your analyte intentionally, and you can break apart organics. It's kind of like a poor man's tandem mass spectrometry experiment. It's called in-source decay, but it's a way for you to derive some information about structure that you may not have otherwise. So we're not the first group to pioneer laser desorption mass spectrometry. Some of the more fundamental advantages of that analytical technique have been appreciated for a while. And so one way that we try to convey this, at least the MOMA team has tried to convey this, is access to more refractory organic compounds. So whereas pyrolysis limits you to things that can enter the gas phase in your pyrolysis experiment, derivatization kind of helps to make things that are less volatile become more volatile. So it kind of gives you access to things through a pyrolysis experiment if you have the capacity to fly a derivatization agent. But what a laser system's used for, again, even in the commercial realm, is to look at more refractory organic compounds. And again, I'm a geologist. It also gives you mineralogical information, which I'm about to show you. So here's some data. It's not just me waving my arms at you, telling you all this cool stuff it can do. We can show some data that highlight the value of laser desorption mass spectrometry. Here are data collected with a proof of concept analog to the MOMA flight instrument. So this is a linear ion trap like MOMA interfaced to a pulsed laser system. And here we have, I'm calling them synthetic planetary analog samples. They're natural rocks, right? So here we've got 2 basalt samples and a nontronite clay from the Clay Mineral Society. These are real samples, but we've doped them with perchlorate. If you're a Mars aficionado, you may know that the surface of the red planet is kind of littered with perchlorates, which complicate the analysis, the detection of organics from pyrolysis. If you pyrolyze something that's got a lot of oxychlorine species in it, you tend to combust the organics down to like CO2, for example. And so a laser source has an advantage that the pulsed laser is like 5 nanoseconds. Our pulse width is around 5 nanoseconds. MOMA is around 2 nanoseconds. Whereas a pyrolysis experiment can last many minutes as you slowly increase the temperature of that aliquota sample. The advantage of having a really short burst of energy, of light to ionize your sample, is that you can effectively see through the perchlorate. And that's what you see here. So regardless of what the inorganic lithological matrix is, basalt or clay, we can see the organic that we've doped, so we know what's in there. We've got 10 parts per million of rhodamine 6G. It's not the most exciting organic compound, but it's a reference material that's been very well characterized. We can effectively see through even weight percent levels of perchlorate because of that pulse laser source. That's one of the reasons, that was one of the key motivating factors of making sure MOMA was capable of an LDMS experiment. It's also capable of doing pyrolysis as well. It's not all honey and sugar and candy. There are some challenges. For the MOMA instrument, I'm a geologist. I love it. I love seeing, if I see an organic, I want to have information about the mineral that was hosting that organic. So that's very exciting for me. But when you have a specific type of mass analyzer, you might, and you're an astrobiologist, you might be less excited about all of this inorganic stuff. So we have all this low mass stuff. Again, these are the samples we made. So I know that these are low mass peaks that represent the inorganic rock or mineral that we're putting, or that we're doping with an organic. So the limitations are that these inorganic signals are taking up volume, ion volume in our mass analyzer. So it's kind of compromising a little bit our dynamic range for organics, our sensitivity to organics. On top of that, the MOMA experiment's further challenged, but you can see that what's the mass range of these inorganics? It's kind of between 150 to 250 atomic mass units. Those aren't elemental signatures. Those are clusters or recombined compounds that represent the matrix, but they're not the matrix. And so it's challenging to understand what this stuff is with a limited mass resolving power. So all of that has served to provide motivation to my team to innovate a laser desorption mass spectrometer centered around an Orbitrap mass analyzer. And so with this combination of hardware, we can achieve ultra-high mass resolving powers, again, to separate those isobaric interferences. Orbitraps are also capable of parts per million level mass accuracy. What does that mean? That means when you see one of your super skinny peaks, you know what it is. You know what the chemical formula is. And then on top of that, it's, in the commercial realm, it's a dual polarity instrument, which sounds maybe trivial or obvious, but MOMA and SAM, they're not dual polarity instruments. So we really haven't taken advantage of dual polarity operations yet for spaceflight. So here's an image of our instruments. This is, I actually have a slide and a couple of slides. I'll show you like the increase in fidelity of the different models that we've built throughout the years, interfacing an Orbitrap to a laser. This one's like our intermediate fidelity model. So I would call this like, what would I call this? I guess you'd call it like a breadboard prototype. But you can see the scale here. I've got a dime that shows the size of the Orbitrap analyzer. If you're not familiar with it, it's a very small analyzer. And we've interfaced it to literally the simplest stack of ion optics that we could design to meet the objectives of the experiment. Trying to really make this as simple as possible to maximize the science in the smallest, lowest risk package. And so this is, I don't have a ton of money to make really awesome graphics about how the instrument works, but Thermo does. And so this is a cool graphic that you can, it's an Orbitrap Elite, so you can steal this from YouTube. It's publicly available, but it kind of shows how the instrument works. It's a little bit different than other types of mass spectrometers that actually like collect the ions that you're trying to analyze. Here you're oscillating the ions around a football-shaped electrode, kind of like it's playoff time. I'm thinking very football. It's very stretched out football, but the ions oscillate around that electrode, and the speed at which they oscillate is correlated with their mass to charge ratio. So you actually kind of just watch them go back and forth, and then you use fast Fourier transform to give you the frequency and thus the identity of that mass to charge ratio. So it works a little bit differently. Okay, so here's kind of a cool slide that shows like the progression in fidelity. So I had an opportunity, essential to this team is a partnership between the University of Maryland, where I'm from, NASA Goddard Space Flight Center, where I came from and where a lot of my colleagues are, and a consortium of French laboratories that have been trying to ruggedize the Orbitrap even before I knew what an Orbitrap was. And so together, along with Thermo, we've all been trying to work to the same end to try to increase the maturity of a variety of instrument concepts. Actually, I can talk afterwards about some other research lines, but trying to get an Orbitrap into space because it brings a lot to the table in the realm of, pharmaceuticals is probably where Orbitraps are most prevalent, but all of those analytical advantages translate directly to astrobiology and even to geochemistry. So this is a picture that I had an opportunity when I had an opportunity to visit my colleagues in France. And so this is kind of like the first proof of concept instrument of a laser interface to an Orbitrap. you can't really even see the whole instrument. It's kind of big. There's a lot of what we call ground support equipment, GSE, enabling that experiment. It's not made to reproduce the form, fit, and function. That's NASA vernacular right there. It's only meant to reproduce the functionality, to show you what the experiment can do. And that's exactly what that platform allowed us to do. Then we built this, what I called it, an intermediate breadboard prototype and this is at NASA Goddard is where this is housed. It meets the form and the function. So we get data that look like what we would expect from a flight model, and the guts look like the flight model. That being said, it doesn't have the whole mechanical package around it that I can put on a vibration plate and shake it and show to you that it's not going to break if you send it to Europa. We're building that though, right? So we're building a couple of Protoflight models that will be able to be qualified end to end for space flight. I'm showing a CAD here, so maybe you're not convinced of how far we are. We're actually building this up. This is one permutation of our instrument. We are building this up. We do have hardware. This is the analyzer with a little black box over the more proprietary parts of the analyzer. I wanted to put a real picture of hardware in there, but this is getting built up right now. We're in the final integration and test phase. So we should have more photos coming up soon to show you that we're actually building this thing. But this is going to be done it's going to be fully qualified by the end of the spring. So we've got it going through thermal cycling, vibration, and then performance testing. And even DHMR for those who are into planetary protection. We're going to do dry heat microbial reduction to show that this instrument can be baked to 115 for whatever it is, 60 hours, because we want this to go to an astrobiological, potentially habitable destination. In addition to ruggedizing that Orbitrap, which I've spent a lot of time talking about, we've developed several ultra compact pulsed laser systems. In this CAD, you see a 213 laser, or a 266 laser, I'm sorry. It's a little bit smaller because it's a fourth harmonic, but we're also developing a 213 nanometer laser that is a little bit better for breaking apart rocks. And so it depends on what your destination is, but we envision this going to ocean worlds like Europa, Enceladus, et cetera, as well as rocky planetary bodies such as the moon. And so we're characterizing these laser systems. They're getting integrated with the analyzer, and they bring a lot of science to the table. Something that's kind of cool about our instrument is that it has a little MEMS mirror inside of it. So we can actually scan the laser beam across the sample and derive a 2D chemical image. That's nice. That's really cool. In the commercial labs, like usually you have like an XY stage that can translate your sample. That'd be great to have on, the Europa lander mission, but that's more mass, more power, more failure modes. And so we're not taking anything for granted. We're having an internal capability to derive a 2D chemical image. So that's kind of one of the neater things about the instrument. So I think I've highlighted a lot of the science that we can get. I'm willing to talk to you about anything that you're interested in doing and whether or not it can be approached with LDMS experimentation. But the one line I will draw your attention to is the last one here. So again, we've tried to pioneer, to begin with, I should say, the simplest instrument, which is just a laser, just an Orbitrap, and the simplest set of ion optics interfacing those two subsystems. And the reason we do that is because it's smaller than an 8 kilogram instrument, and the peak power is on the order of 40 watts. So it's a very relatively easy to accommodate instrument that, again, brings a lot of science return to the table. So the last part of my talk, let's see, I'm at 1:30. Ooh, that's not too bad. So I've talked pretty quickly. That saves me more time. Good. Applications, right? So this talk is a little bit backwards from the way I usually introduce what we do, but that's because I want to end with some of the really cool data that we've collected as in the last couple of weeks and months. And so here I've kind of like started with the technique and the analytical instrument or method. And now I kind of want to go into applications, which otherwise might have been thought of as motivation. So it's a little bit of a flip. But again, this is the NfoLD community. So you guys are probably experts in ocean worlds beyond me. But I like to highlight, I teach a course in planetary habitability, and this is one of the slides I go over it. But I like to highlight also the historical perspective. I'm not going to go into that in this talk about how ocean worlds have come to the forefront and how opportunities for exploration of ocean worlds have been elevated more quickly than traditional. So more quickly than, for example, finding their way into the NASA Decadal Survey. There's a lot of history there. And a lot of you may be part of that history and know it better than me. But what matters is that the more we learn about a lot of these cryogenic planetary environments, the more excited we get, because we see whether chemical ingredients or disequilibria or morphological evidence for exchange across the ocean ice interface. We see a lot of characteristics that get our pulse accelerated, that there could be a habitable environment, not just in the past, but there could be a habitable environment now on a variety of these ocean world environments. And so there's a lot of excitement to exploring these. Okay, so let's say you buy that, right? You buy that there's maybe all of your favorite top 10 things, ingredients, factors, parameters that you think are required to define a habitable environment. Okay, let's go there and let's look for signs of life, right? Network of life detection. What is going to convince us that we've detected life or not? That's an ongoing discussion that NfoLD's been really leading the community towards. And it's a very healthy discussion. It's a very healthy argument as to how you might rank different physical or chemical observations on a scale of confidence as to whether or not they're compelling, compelling to be biologically derived or abiotically derived. That's probably like 3 or 4 or 5 or 100 more NfoLD seminars. In fact, some of you guys probably participated in that workshop that NfoLD and Nexus, which is another research coordination network, hosted this past summer. And maybe you all have seen the invitation for NfoLD's, I guess it's another workshop, right? It's 2 5-day workshops talking about life detection science, followed by life detection engineering. And so there's continues to be this evolving discussion about what are biosignatures, which biosignatures provide us the most confidence, most information about whether or not we're looking at something that's truly representative of life or not. And so the reason I'm like harping on this is the easy answer. Yeah, I'm going to give you an answer. The easy answer is have access to as many of these prospective biomarkers as possible. When you have as much information as possible, then you're going to have the greatest confidence. So instead of arguing potentially over which one of these different biomarkers it provides you personally with the most confidence that you're looking at something biological, we want access to as many as possible. And then we can feed into things like molecular complexity and use machine learning to maybe take out the human interpretation of what's going on. And that's what I'm going to try to show you that laser desorption mass spectrometry can do. It actually provides us access to a wide range of biosignatures. So when I had the opportunity to go to France, we were just kind of trying to show very much proof of concept. What can this instrument do? And so again, we made some synthetic analog samples. So in this case, in the upper left, get my little laser pointer here, you can see that we had some magnesium sulfate that we doped with valine just to see, can we see both the organic and the inorganic? Can we empirically prove, justify what I've been like railing on for the last, 40 minutes? And so we were able to see it, right? So here is a spectrum we collected on that French prototype instrument where we can see the molecular ion. We can see a characteristic fragment. It's the same fragment that if you go to the NIST web book would be what you would expect to be the dominant fragment if you were also analyzing this with a 70 EV electron ionization source. And then fun fact, we can see the inorganic information. And if you're familiar with the periodic table, you'll also see, oh, you can also see the diagnostic isotope abundances of magnesium. Sulfur is a little bit harder to see, but now you're starting to see the range of information. We have the inorganic context, we have the organic, we start to get information about fragmentation, which can give us information about structure. This is easy. We know it's veiling because we doped it, but looking at fragments that come off can give you a corroborative evidence of what's in there. And now we are starting to explore the trade space of what kind of isotopic precision can we get with this instrument. Detection limits. Everyone wants to see detection limits. I don't have that data set for you because detection limits are going to be very specific to the experiment. It's going to be very specific to the analyte. Things that are easy to ionize with low ionization energies make your detection limits look pretty good. Things that aren't easy to ionize, like amino acids, which have ionization energies around 8 eV, are a little bit harder to ionize, but they're more relevant for astrobiological purposes. And so when we were in France, we used, your typical Sigma, Aldrich, Waters amino acid solution, diluted it and dried it down onto a plate. Just like we might envision a Europa or an Enceladus lander gives us an aliquot of ice. We allow it to sublimate, and then we look at the residue. And what we're able to see is that we're able to see a wide range of amino acids at a weird surface concentration. So this isn't like weight percent, because this is a surface technique. We need to have like moles per unit area. The relevance of 1 picomole per millimeter squared is that's like the pass-fail criteria for MOMA. It's not MOMA's detection limit. As I said, detection limits are specific to an analyte and specific to the experiment, but it's like their pass-fail criterion for their different models, right? Their engineering test unit, their flight model, their flight spare, et cetera. That's kind of like their bar to allow for a comparative analysis of their different models. But we wanted to see, can we see those same signals? And we were able to with our French instrument. Minerals, okay, let's start making this a little bit more complex. What about if we've got, I don't know, a basalt? If you're a geologist, you know what a basalt is. Actually, maybe everyone knows what a basalt is. Maybe you know what a komatiite is, high degree partial melt. What if we dope those with amino acids or any other of your favorite potential biosignatures? This is kind of the trade space that we have been and we continue to live at, because we want to convince ourselves, and by extension to convince the community, that we can understand the geological context of any putative biosignatures that we detect. So with the instrument at NASA Goddard Space Flight Center, my team, including my former student, Lori Wilhite, and my current postdoc, Anais Bardin, some of you guys may know, one or more of them, have been trying to characterize some other performance metrics of the instrument. So the reproducibility, here we've got cesium iodide spectra, a whole bunch of them in a row. Cesium iodide is not particularly exciting for astrobiology, but it's our calibrate. It's also MOMA's calibrate. So it's a good baseline to understand the reproducibility of the experiment. We're starting to look at more realistic ocean world samples. So here we've got a solution that's got 0.3 weight percent potassium chloride, and we're starting to get, I'll say, more realistic. It's still kind of enriched, but more realistic concentrations of a variety of biomarkers we're interested in to look at how do these biomarkers manifest in an LDMS spectrum. Do we see the molecular ion? Do we see it protonated? Do we see it potassiated? Do we see the diagnostic fragment? Can we see the isotopic composition of the inorganic matrix, etc.? What kind of quantitative information can we get? Can we infer the abundance, the relative abundance of thiamine to histidine, or potassium to some impurity in that salt? A lot of work has been and continues to go into this. Isotopes, what's the reproducibility of our isotopic precision? And so here's another picture of Grace. What she's been kind of leading is to consider less conventional ways of using an Orbitrap to derive more information about the sample. And so there's a growing, slowly growing, it's like a snowball effect. It's slowly growing community looking at what happens to those ions when they're inside the Orbitrap. Eventually that signal decays away, right? Because it's imperfect vacuum, it's an imperfect squeezed football because, you know, someone's got to machine it. You've got other ions in there that are competing for that volume as well. So there's a decay rate of the signal intensity for everything that's in there. That decay rate can also give you information about what that molecular identity is. And so Grace and others have been trying to understand, it's kind of like an ion mobility experiment. Can you derive a corroborative measure of molecular identity? And then on top of that, could you do something even more exciting, like, I don't know, distinguish structural isomers that might have different collision cross sections because of the way the atoms are arranged in that compound. And then on top of that, in-source decay is something that we're trying to empirically show, rather than me just tell you that it's really cool. We're trying to show, crank up the laser on purpose, intentionally break down the organics in there, and look at the fragments and get that de facto MS-MS spectrum. So something kind of newer that we've been doing is teaming up with some partners at the University of Washington. People like Brooke Nunn and Karen Junge, if I'm hopefully pronouncing her last name right. I'm terrible with last names, but mine's hard too, so I feel like that's fair. And they're I would argue, they'd probably disagree, that they're closer to being traditional astrobiologists, classical astrobiologists. So they're like microbiologists, and what they and their team at University of Washington and their partners have been doing are studying extremophiles. And so they've been, you know, they're interested in this one in particular, Colwellia. I'm not going to pronounce it. I'm going to call it CP34H. Actually, I'm just going to call it bug. They're looking at this particular bug that's found in Arctic marine sediments and Arctic sea ice. And this bug is interesting because it can survive extremely cold temperatures and extremely high salinities. And so this microorganism could represent a terrestrial analog to something that could survive on Europa or Enceladus or these other potential ocean worlds. And so what they've been doing is not just, you know, collecting this bug. They've been collecting this bug, and then they're probably going to make fun of me how I'm going to butcher what they're doing. But what they're doing is they're really growing different cultures of that microorganism, and then subjecting those cultures to even colder temperatures, to the highest salinities for, you know, here it was 4 months for this most recent publication they've been working on. And then the cultures that survive those exposures, they're looking at the proteomes. So they want to see if there are any proteomic signatures, or in the case that I'm going to share with you, short peptides of 3 or 4 amino acids that are statistically enriched in the cultures that survived exposure to the coldest temperatures, in the cultures that survived exposure to the highest salinities. Because those peptides, those proteomic signatures, could be what allow those cells to survive the most extreme conditions. And thus that might be something that's shared with alien life in other cryogenic planetary environments. And so, of course, they've done the statistical analysis, and they found a wide variety of 3 and 4 amino acid polypeptides that are correlated with the incubations at the coldest temperatures and the highest salinities. And so the next step was, okay, that's cool. First of all, that is cool. I love the work they do. It's so interesting. But then they were like, they asked, I remember Brooke accosted me at the last AbSciCon and said, can you measure, this is without any context, can you measure tripeptides? And I was like, I don't know, I haven't tried it. And so finally, over the last few years, we've built this collaboration together, and that's exactly what we've done. So using Brooke and her group's research to identify those prospective peptide biomarkers, we had a company called Biometic that can synthesize these peptides in relatively pure aliquots. We put them in water and a little bit of formic acid. We kept it to the simplest matrix possible because I didn't want to worry about any matrix effects. We dried them down and we interfaced them to our instrument, that intermediate fidelity breadboard instrument at NASA Goddard Space Flight Center. And we wanted to see if we could detect it. And so I'm going to give you one slide here because this is so new, but it's exciting enough. I want to share it. But here are two of these peptide signatures. You can kind of see where they're highlighted. There we go. AAG, which is associated both with the lowest temperature and the highest salinities, and then SKSR, which is associated with the high salinity, and then these other brine conditions. So you can kind of see this Venn diagram. And so it's a 3 and a 4 amino acid peptide. Can we see them was the first question. Can we see the molecular ion? That would be cool. But for this to actually be a useful biomarker and for LDMS to be a truly viable analytical technique to identify this biomarker, we kind of need to sequence it because AAG is very different than AGA. AGA is not statistically enriched in these microorganisms subjected to extreme conditions, but it's going to have the same molecular weight. So we want to see the molecular ion, but it's really being able to sequence it that's fundamental for this biomarker. And so I had to learn about how to do de novo peptide sequencing. What are the fragments that come off? Which bonds have to break? And which fragments do you need? Like, what's the minimum set of fragments that you need to observe in order to reconstruct, in order to sequence that peptide? And so here's the single spectrum I'm going to give you because this is so new, cutting edge, and for us. But the takeaway is that we're able to see the molecular ion of both of these. This is a combination, right, of both of these. And we're able to see a variety of fragments without, the cool part, without applying a matrix to the sample. So typically in a commercial lab, for example, you might apply a MALDI matrix, if you've heard of the acronym MALDI, matrix assisted laser desorption ionization. We don't want to have to fly an organic to Europa or Enceladus to look for organics. So we're trying to see what we can do with our instrument without having to do that yet. We are exploring inorganic matrices because it's not such a big deal to fly nanoparticle silver out there because, we know we're bringing silver, and maybe it's less controversial to fly silver to a potentially habitable world. But first, we're trying to understand what our instrument can do. And we can sequence at least a subset of the peptides that we've had the opportunity to analyze with our prototype instrument that meets the form and function of a flight model. We're able to see the molecular ion, we're able to see diagnostic fragments, and we're able to actually sequence these peptides. Okay, so I'm running out of time here, but the applications aren't limited to ocean worlds. There's been an opportunity to think about the moon, both as, in my case, a classically trained geochemist, but also as an amateur astrobiologist. And so with Artemis comes opportunities to, for example, mature your instrument by sending it to the moon. And if you have that opportunity, you're going to want to collect as much science as you can over those, depends how long that mission is. But this most recent PRISM call, if you're familiar with the lunar program, there was an opportunity very recently that we responded to. It closed on December 20th to send payloads to the lunar surface to one of 2 different candidate landing sites. And if you do that, you're going to try to get as much science as you can over that 8 or 9 days before you enter, before you get in the shadow and your payload freezes to death. And so with this commercial, with NASA's emphasis of enabling commercial partners to land payloads on the moon to support the Artemis program, there's an opportunity for us to collect science. And the moon's pretty exciting. There's a lot of science there. As a geochemist, you guys might not be interested, but I'm going to tell you what I'm interested in. As a geochemist, I'm interested in understanding the composition of the moon, like fundamentally. So the abundance of refractory and volatile elements in the moon, surprisingly, after decades of research, is still kind of not well resolved. And so understanding ratios of those elements, like quantitatively, we know the moon's depleted in volatiles, but understanding quantitatively the magnitude of volatile element depletion. And is there an enrichment in refractory elements? That goes to like the basics as to how did the moon form, right? If there was a major moon forming event, where did the volatiles get lost from? Where did they reaccrete? Was there incomplete condensation? Was there volatile loss? What are the mechanisms of that volatile depletion? What I think we in this community are interested in is also considering the moon as a witness plate, right? There's exogenous infall onto the lunar surface every minute of every day. And so carbonaceous chondrites can have weight % level of organic matter in them. And so understanding the distribution of organics that have accumulated on the lunar surface, maybe even the preservation of those organics upon emplacement from exogenous infall, and certainly the diversity provides what I would call, and I think others would agree, is like a life detection blank. It's kind of comprehensive. Maybe it's not a perfect apples to apples comparison with the infall of material on a satellite in the outer solar system, but it certainly gives us more information about what might otherwise be considered, what might otherwise be a false positive. And then finally, there's a lot of the community is interested in looking for resources on the lunar surface. So this is, I think, my last slide before the conclusions. My team put in so much work to think about how we could implement one of our instruments, one of our laser desorption mass spectrometer instruments centered around an Orbitrap onto a lunar commercial vehicle, access material on the surface. So here is what we envision doing, putting our instrument on the deck. I think this is Astrobotics Peregrine, just as a kind of like a placeholder. And then flying with us the simplest articulating arm, because arms are risky, I get it, but this only has 2 degrees of freedom, but it's really just a scoop to bring sample to our instrument so that we can analyze it. If you have the capacity, and this PRISM opportunity did, to also take advantage of mobility with a lunar rover, we could have a complementary instrument to allow for that corroborative identification of sample composition, also to increase the diversity of the measurements that we're able to collect. So we envision putting our LDMS instrument on the lander and a gamma ray spectrometer on the rover. And with taking advantage of that mobility, we can analyze features of the lunar surface from the nanometer scale, which is like a single laser shot, all the way to the kilometer scale. So it's a really exciting investigation. We hope we get selected. It has astrobiological implications to it, but it kind of shows that LDMS techniques aren't just limited. I don't want to say limited, I hate that word. They're not pigeonholed to looking for signs of life. It's certainly bread and butter for LDMS techniques, but because a rock, major rock forming elements have ionization energies at, or in some cases below, many biosignatures, we get that information for free. And so with that, I'll leave you with the take-home messages. They're bulleted up here, so I'll stop rambling and hopefully have 6 minutes, 6 juicy minutes for questions or comments if there are any out there. Thanks for your time.
Thank you so much, Ricky. This is really, really, really interesting. Wow, there's a lot more you could do than I thought. Just phenomenal. So the floor is open for questions. I think you already have one in the chat.
I do have chat here.
Yeah, I think Mark is the first one. I can read for you if you want. Will it be possible in the future to detect trace molecular compounds at a ppb or even ppt level?
Of course. There are many answers to that. So the answer is going to be yes. Again, so our sensitivity, our detection limit, I'll say, in well, I guess it's probably true for a lot of analytical techniques, is going to be controlled by the ionization energy, and maybe in our case, the desorption threshold of the sample. If you wanted to see something below the volume or weight concentration that, you know, that we have shown or that we can show. You know, another answer might be, at least for an ocean worlds permutation, you could sublimate more sample, right? So we were trying to understand, you know, so the Europa Lander STT, for example, says that every instrument gets, I think, 1 cubic centimeter of ice. And so how you can sublimate, so because we like the residues, we're more sensitive when it's a residue. We can look at the ice if you want us to, but certainly the detection limits are better when you can sublimate that material. But if you were able to sublimate 2 cubic centimeters, you've just improved your detection limit, presumably by a factor of 2. And so there's a trade-off there as well. I don't know if I'm dancing around the answer because I've got so many things going through my mind. But feel free to ask for clarification if I'm dancing around it.
Thank you. Owen Lemur has the next question. He asks, could you say a bit more about LDMS, about how LDMS compares to LIBS and landmass measurements?
I can.
In a minute.
Oh, could I? Yeah, so I think the challenge for LIBS, so LIBS, I was thinking Raman, for example. So LIBS, right, you look at the light from the plasma and you can get information about the elemental composition. I'd say LIBS has done, we're all challenged with calibration. LIBS spectra are challenged to calibrate / quantitate elemental abundances, but they're probably ahead of where we are. We have shot-to-shot reproducibility too, but that's TBD. So we have, you know, I have a new postdoc in my group, and we've been interested in a long time for exploring the quantitative capabilities of just a laser source with nothing else on it, no plasma source on it. And so I'll be curious to understand what our reproducibility for elemental abundances are, because lasers, for 30 years, we're well aware that lasers incur elemental fractionation. Can we calibrate for that with LDMS techniques, and how well is TBD. So right now, I don't want to give an apples to apples comparison. I can say from a detection limit, so we were trying to understand this too for our lunar proposal. And so we looked at NIST. I don't know if you're a LIBS person, then maybe you're familiar with NIST 610. It's a standard reference material. And based on a very cursory, like we kind of threw it in our instrument on the last day that we could collect spectra for our proposal. And we were able to see rare earth elements down to 5 ppm levels. But we haven't really pushed the envelope yet. We didn't try NIST 612, which is 10 times less than that. And that was with the 266 laser versus the 213, which certainly couples better with optically translucent glasses. So I think we're going to be able to get down into the parts per billion trace element abundances. So that already gives me confidence that we'll be able to see parts per billion organics as well. It's just, we typically think about those and being in these residues. But I don't know, I'm rambling again. I'm going to end there. So I'm going to say that we're approaching this parts per billion level detection limits. I think that's where not a lot, but that's where a number of elements are in the LIBS detection limits as well. Now Lammis, I'm less familiar with firsthand, so I don't want to speak out of turn for that.
Thank you. Cole Mattis has his hand up. Cole, you want to unmute?
Yeah, thanks. Great talk. I had a couple questions that I'll throw at you, and you can sort of answer what you think is interesting. The first set of questions is basically just like this. Well, the most relevant question is, what's the upper range on the mass limit, right? So I think everything I saw today, the highest number I saw was like 500 AMU. Obviously, you have an Orbitrap, you could go higher than that in principle. So my question would be, what's the upper range, do you think? And is that something you could set during the mission? And then more technical questions like this Orbitrap that you built, how does the geometry of that sort of differ from what you would see in like the off-the-shelf instruments that you buy from Thermo or something? Is it significantly different because you're anticipating attaching it to a satellite, or is it exactly the same sort of geometry? And then I have some other questions about this stuff you were doing with the sort of collisional cross-section and trying to tease out more molecular information. But I'll set that aside because we're already over time.
Yeah, so first one is mass range. It is tunable, absolutely. So when we were getting ready to respond to the Europa lander mission, when it was a mission, we had envisioned carrying multiple experiments. One trying to look at the inorganic stuff, which would be lower mass, and one trying to focus in on the higher mass stuff. And so the SDT, for example, wanted relative abundances of amino acids with respect to glycine, which is 75, right? So we thought, okay, we don't want the salts competing with the ion volume in the Orbitrap, so our organic mode will start at mass 75. The mass range of our instrument and with our Protoflight electronics, which we're trying to reproduce what Thermo can do, but making it compatible with flight means you cut some corners. We can see about 30 to 40x. About 40x is our upper limit from the low mass range. So whatever your low mass is, multiply it times 40, and that's your upper mass limit before you start rolling off in performance. The second one is the Orbitrap just like the commercial one?
Yeah, I'm specifically interested if you've I've seen some stuff where some of these flight instruments, they'll have like a very slightly different geometry than something you would expect to use in a lab here. And I've just been curious about that.
The geometry, I think we've preserved.
Okay.
But certainly everything around it has been beefed up because it's hard to not break it, right? Those ceramics are very fragile. You want them to be quartz because that gives you the best isolation. But alumina buys you more margin on vibration. So it's a trade as to, it depends on the mission, but the most challenging missions, like going to the moon, where you're on a commercial lander that could fail, first of all, but you don't know what the loads are. So you have to qualify it for the max GEVS level. Anyway, the infrastructure around it is certainly different than a commercial instrument, but the core analyzer, the geometry is more or less the same.
And just the last thing to throw out there, if you could say any more about what you're doing with this sort of collisional cross-section to try to tease out more molecular identification. And are you approaching that from a purely sort of like empirical, like let's just see what we can get out of all the data, or are you trying to do any sort of modeling at the scale of ionization and sort of interactions in the trap?
Would you mind if I jump in here? Because we had one more question, Paul, which is a good question to ask, but I'm hoping you can connect with Ricky afterwards. Because we're at the top of the hour, I want to make sure everybody got a chance to ask a question. The last one is from Esther Munoz, who asks, could you briefly discuss how the laser ablation may or may not affect the stable isotope measurement of our sample? And that will be the last question for today.
Yeah, so we have empirically seen, we have not observed fractionation, stable isotope fractionation. So we looked at potassium, for example. When I went to France, we were looking at potassium isotopes in jarosite, I think was the sample that we were looking at. But we've got magnesium isotopes too. We did not observe fractionation, but our error bars aren't as fine as some, right? So we're trying to, and we did meet for potassium, I don't remember magnesium, but for potassium, we met the SDT request for 10 per mil, and we did that external reproducibility. So internal, you can always make your numbers look pretty good, but we wanted to understand the external reproducibility because every laser shot gives us an independent mass spectrum. And we were able to meet the 10 per mil metric that the STT wanted from a 2 sigma perspective. That being said, if we're fractionating, some degree smaller than 10 per mil, we wouldn't see it. So within our external reproducibility, we did not, that we saw terrestrial, and which is what we would expect. We are trying to understand fractionation though. So this kind of goes to Cole's question as well. I'm an empiricist, kind of. I tend to want to test everything out and then figure it out afterwards. Grace, I don't know if you know Grace. She's the one whose picture I put up several times. She's been simulating it. She wants to know what the heck is going on in there. And because she also wants to know what's possible. right? Because we might not have a tuned instrument. So she wants to know, what if there's noise? What if there's more than one ion packet inside? What if you've got space charge issues? What if you've got, and she's trying to understand, like, in the best case, what's the uncertainty on those collision cross sections? Because we want to know, ideally, can you resolve structural isomers that might have really small differences in the collision cross sections? So she's approaching it from a simulation and a modeling standpoint. But we have, I think I showed some empirical data that we've worked with on our instruments as well. So it's trying to unify it. But I think the modeling will give us an understanding as to why the error bars are so big right now. And right now they're too big to separate structural isomers of interest to us. But that being said, we're also trying to look, the reason I'm trying to connect these questions, we're trying to understand if there's fractionation in the analyzer for isotopes as well, right? Because, you know, maybe the collision cross section is not different, but maybe the lighter mass is in closer proximity to a mass charge violation than the higher mass. And so we're looking at the transients and doing slicing and all kinds of windowing and all this other stuff to see, are we fractionating in there? The laser we can probably calibrate for, even to like really fine degrees. I mean, if you've got a multiple isotope system, I think you can calibrate for the laser, but what happens inside the analyzer may be more challenging for us to calibrate for.
Great. Well, thank you very much, Ricky, for a really, really interesting conversation and talk. I learned a lot, and I hope all of you have as well. Thank you for connecting to this NfoLD seminar. Again, we try to have those every 2 months, but if you are willing to give us a presentation next month, please let us know at contact.nfold@gmail.com. Thank you very much for connecting today. And Ricky, you know, really grateful for you taking the time to chat. This was really, really very interesting. So lovely.
Thanks for the opportunity.
Oh, you're most welcome. With that, take care, everybody. Thank you for connecting.